All right, today we are diving head first into the deep end. We're going right to the very edge of human knowledge to tackle the questions that have even the smartest physicists in the world just staring into space. These are the biggest, weirdest, most fundamental mysteries out there. Let's get into it. So let's just start with this absolute mind bender of an idea. The very fabric of reality, the space and time we all exist in, might actually be woven together from a massive net of tiny, microscopic wormholes. Yeah, exactly. What in the world does that even mean? Well, that's what we're here to figure out. We're going to break down the puzzles that keep the world's greatest minds up at night. And we're starting in one of the most violent places in the universe, the heart of a black hole. Okay, our first stop, the singularity. This is supposed to be a point of infinite density, where our entire understanding of physics just completely falls apart. And the whole problem starts with one of the tiniest things we know of. This right here is the question that just breaks everything. See, in nature, we never, ever see a quark all by itself. They're always stuck together by a force that is, frankly, bizarre. So what happens when you throw the insane gravity of a black hole into that mix? Well, things get really, really weird. So this force, it's totally backwards from what you'd expect. Unlike gravity or magnetism that gets weaker the farther you go, this thing gets stronger. The more you try to pull two quarks apart, the harder they snap back together. It's almost exactly like stretching a rubber band. So, just imagine this for a second. A black hole's gravity starts pulling on that quark rubber band. It stretches, and the energy in that band gets more and more intense until, snap, it breaks. But here's the crazy part. All that energy, thanks to good old E equals mc squared, has to go somewhere, so it instantly creates a brand new pair of quarks, and that process could just keep repeating itself over and over in a massive chain reaction. This quote just nails the problem perfectly. That kind of infinite runaway energy reaction is what our math tells us should happen. General relativity, our best theory for gravity, literally predicts that space-time becomes infinitely curved at the center. It's a mathematical absurdity. It's like asking a calculator to divide by zero. The laws of physics just stop working. So how do we get around that? Well, some physicists have come up with some pretty wild ideas. One of them is the fuzzball theory. It suggests there's no single, infinitely dense point at all. Instead, a black hole is just a big, tangled, fuzzy ball of stuff. This neatly avoids the whole dividing by zero issue, but yeah, for now, it's still just a very cool idea. All right, let's shift gears to our next big mystery. This is something that's all around us. It makes up most of the universe, but we can't see it, touch it, or feel it. We're talking about dark matter. We know it's there because of its gravity, but what is it? Well, to understand the leading theory, we actually have to look back in time a bit. You see, there's a history here of physicists basically inventing particles to fix their math. Back in the early 1900s, they noticed that energy seemed to be just disappearing in certain reactions. The numbers didn't add up. So this guy, Wolfgang Pauli, makes this incredibly bold suggestion. He says, maybe there's an invisible particle carrying away that missing energy. He called it the neutrino. And look, it sounds crazy, right? Just making something up. But as Neil deGrasse Tyson says, sometimes geniuses make stuff up and it turns out to be right. Because decades later, they actually found it. They detected the neutrino. And that history is exactly why scientists are so willing to propose a new, undiscovered particle to solve the dark matter problem. Now, the most popular, most beautiful idea for what dark matter could be is called supersymmetry. It's this incredible theory that suggests there's a hidden symmetry in the universe. It says that for every single particle we know about, there's a heavier, secret superpartner out there. Think about that. The idea is just huge. It basically means the entire zoo of particles we know is only half the story. So for our electron, there's a selectron. For a quark, there's a squark. Supersymmetry basically predicts a whole shadow universe of particles hiding just out of our sight. So why did physicists absolutely fall in love with this idea? Well, it's not just a wild guess. First, it just so happens to solve a whole bunch of other annoying problems in physics at the same time. Second, the theory predicts that the lightest of all these new superparticles would be perfectly stable because it would have nothing to decay into. But here's the real kicker. When you do the math and calculate how much of that leftover particle should have been created in the Big Bang, the number is a perfect, dead-on match for the amount of dark matter we actually see in the universe today. It just felt like it had to be right. Which brings us to the big, frustrating question: where is it? For years, everyone was convinced that as soon as we built a big enough machine, like the Large Hadron Collider, these super partners would just start popping into existence. But they didn't. We have found absolutely nothing. Not a single one. And this is a huge problem. Our most beautiful, most elegant theory for what makes up 85% of the universe is a complete no-show. It points to a deep, fundamental crack in our understanding of things. Which, funny enough, brings us right back to that crazy idea from the beginning about what space itself is actually made of. To understand this, we need to talk about quantum entanglement. This is that famously spooky thing Einstein hated, where two particles can be linked across the universe. You poke one, and the other one instantly reacts, no matter how far apart they are. For the longest time, we just thought it was a weird quirk of the quantum world. But now, physicists are working on this incredible new idea. They're finding that entanglement, this quantum connection, and a wormhole, a tunnel through spacetime, might actually be the exact same thing. They're just two different ways of describing one reality, one using the language of quantum mechanics and the other using the language of gravity. The implication here is it's just staggering. It means space and time aren't the fundamental backdrop of the universe. There's something that emerges from all these quantum connections. Like Brian Greene says, if you could somehow go through and cut all these little quantum threads, space itself would just fall apart. It would cease to exist. Okay, so if supersymmetry not showing up is a crack in our theories, this final problem, this is a gaping chasm. We've now arrived at what is probably the single most profound and deeply embarrassing failure in the history of science. It's a mystery about the energy of nothing at all, the energy of empty space. So, on one side, you have quantum mechanics. Let's be clear, this is the most successful, most precisely tested theory humans have ever come up with. And using that theory, we can make a prediction. We can calculate the amount of energy that should exist in totally empty space, what we now call dark energy. And then, on the other side, we have our telescopes. We can literally point them at the sky, measure how fast the universe is expanding, and figure out the actual amount of dark energy that's out there. We have a real observed number. Here's the punchline. The prediction from our best theory and the measurement from our best telescopes, they don't match. And they're not just a little off. They are wrong by a factor of 10 to the 120th power. That is a 1 followed by 120 zeros. It is, without any exaggeration, the biggest mistake in the entire history of physics. And yet, after all of that, after seeing these colossal failures and paradoxes, there's something incredible to consider. As Neil deGrasse Tyson points out, just think about the fact that we, these fragile little beings with a few pounds of brain matter, can even ask these questions. We've somehow managed to learn the language of the cosmos, even if we can't read all the pages yet. You know, being this spectacularly wrong isn't really a failure. It's actually a triumph. It means we know enough to know how much we don't know. It's a giant signpost, pointing us toward a deeper, truer reality we just haven't figured out yet. And that just leaves you wondering, what's the next great cosmic secret waiting for us right over the horizon?